This is projectile motion example number 4. If we notice that this one is not going to be horizontal launch. Connor kicks a soccer ball at 12 meters per second at an angle of 35 degrees. If it hits the ground 1.4 seconds later, how far away did it hit the ground? And then, what was its peak height? As we draw it out, we notice that we are not kicking something off a cliff or off a table. We're actually launching it at some particular angle of, in this case, 35 degrees at some speed of 12 meters per second. Filling in the rest of the information, we will be looking for how high it goes up. That is going to be the peak height. And we should also draw on acceleration due to gravity. And we've also, on over here, that's going to be the displacement on the x-axis or the range. Now, before we start listing out our variables and plugging in, we need to be thinking, because as we can see, this is actually launched at an angle, 12 meters per second at the 35 degrees. So it's not completely on the x-axis or completely on the y-axis. So what I need to do is break it up into my x and y components using my trig functions. Remembering that the x is going to be equaling the r times the cosine of theta, and the y is going to equal r times the sine of theta. Okay, let's go ahead and try out some of those values. Let's see, for my x, because I was asked about the x first, the velocity on the x, my displacement on the x, and then my time. So as we said, we're going to be using r times the cosine theta, so that's 12 meters per second times the cosine of 35 degrees. It gives me, tapping into my calculator, 9.83 meters per second. My displacement on the x-axis is what I'm looking for, and they were nice enough to give me the time. That was 1.4 seconds. Simple enough, I'm just going to be using displacement on the x equals velocity on the x times time. I can just plug in my values. Displacement on the x equals 9.83 meters per second times the time, which was 1.4 seconds. Displacement on the x, tapping into my calculator, is going to be 13.762 meters. With reasonable significant digits, that would be 14 meters. Now I can do a similar thing for the y-axis. If I've got my list going on for the y-axis, my initial velocity, final velocity, acceleration, displacement, and time. Initial velocity, as we mentioned, we'll be using r times the sine of theta, so that's 12 meters per second times sine of 35 degrees. Tapping that into my calculator, I get 6.88 meters per second. My final velocity, since it's up here at the peak, that's its maximum, is going to be 0 meters per second. Acceleration, as usual, is little g, or negative 9.8 meters per second squared. My displacement is what I'm looking for. Now my time, this is tricky. They give me 1.4 seconds, but that's for the entire time starting from the launching point to my ending point. I don't actually want to use that. I would actually have to use half of that. Now, I could figure that out pretty easily. That's going to be 0.7 seconds. But I might as well go ahead and not care about my displacement, or I'm sorry, not care about my time. So that is going to be the VF squared equation. VF squared equals VI squared plus 2AD. That's nice because the final velocity is going to be 0. That makes this initial velocity squared equals 2AD. I'm sorry, that was negative initial velocity squared. Bringing the 2A to the other side, I have my displacement is equal to negative VI squared divided by 2A. I can now tap into my calculator. That is going to be negative 6.88 meters per second squared divided by twice the negative 9.8 meters per second squared. And my displacement will end up being 2.415 meters, or with sig figs, 2.4 meters. Now, the reason I went ahead and showed you these steps was to make sure that when you're dividing this 6.88 squared, you're dividing by this entire thing, the 2 times negative 9.8. Put that in parentheses, or your order of operations for your calculator might mess up. Anyhow, hooray for physics.